Heat of a reaction tells us essentially heat or gain or loss during a reaction. You can actually think of a number of different reactions that either give off heat, so they produce heat, they're hot reactions, or that absorb heat, so where heat is lost during the reaction. In that case, it feels like the reaction is getting colder if we're holding it or observing it. The heat of a reaction is typically measured in kilojoules, and it's symbolized by the delta H here. So delta just means change in, and so H for enthalpy, or the heat of the reaction. So the change in the heat of the reaction is just essentially a measure of the energy of the products minus the energy of the reactants. If there's more, there's a difference here, we either are going to gain or lose heat. So if we look at an exothermic reaction, the amount of energy of our reactants is much higher than our products. So we have our reactants react, they produce our products, and in the process, this extra energy here leaves. And so we can feel this as heat given off. In the case of this reaction, you've seen this before, this reaction is highly exothermic, so exo meaning exit, so the heat is exiting the reaction, it's being released. So this reaction is kind of fiery, you wouldn't want to hold this in your hand while it's happening, but the heat is coming off of it. In an endothermic reaction, so endo meaning into, our reactants are lower in energy, and we have to put energy in to the reaction to have it occur. So we feel that by feeling that the reaction gets colder, because the reaction is pulling heat from inside of us out. So if we look at that, so that's what we can look at it in the graph form. If we look at it as far as the heat reaction, so exothermic reactions, our delta H is negative. So the actual value of our delta H is negative. If we look back at our formula, it's products minus reactants. So if our reactants are larger than our products in terms of heat, then we're going to get a negative value. So that's going to be exothermic. If it's the opposite, it's going to be positive. So our delta H of reaction of negative is going to be exothermic. You can think about a negative as being like the energy is leaving the reaction. It's getting out of there. For positive, we're adding it in. We have to add in the heat. And that's why it's endothermic. We're pushing the heat into the reaction. Now, we want to look at how we can use these heat of reactions to find out how much heat would be produced from a particular reaction. So, how many kilojoules of heat would be released from the complete combustion of 250.0 grams of C3H8? We've looked at this type of reaction before. Whenever we're talking about combustion or any types of reaction, we need to know what the balanced reaction is. So we need the balanced reaction, and in this case, we also need the delta H of reaction. We're not going to get too much into how the delta H of reaction is found here, but there's a variety of ways that we measure the heat of a reaction. This is how we also measure things like the combustion of different products, how we determine how many calories are in different types of food. There's a lot of different applications for these delta H's of reaction. In this case, if we have this reaction where we have 1 mole of C3H8 and 5 moles of O2 forming 3 CO2 and 4 H2O, if this reaction happens exactly as written, so 1 mole to 5 moles to 3 moles to 4 moles, then we're going to release negative, so it's going to be negative 2,219.2 kilojoules. And it makes sense. Combustions are exothermic reactions. They give off heat. They're fiery. That's, if something produces fire, we would expect it to have a negative delta H. And this does. So That means that for every 1 mole of C3H8, it gives off 2,219.2 kilojoules of heat. So we're going to need moles to actually solve this problem. So we're going to have to go from grams of C3H8 to moles of C3H8. And then we're going to go from moles of C3H8 to our heat. So we're going to go from that to kilojoules. We'll look through this step by step. So I know I have 250.0 grams of C3H8. I can use the molar mass of C3H8 to get my moles of C3H8. Once I know my moles of C3H8, I can then use that I have negative 2,219.2 kilojoules for every 1 mole C3H8. I can multiply that through, and my moles of C3H8 are going to cancel, and I get that I release negative 12,600 kilojoules when I do this reaction with 250 grams. So this could be a very useful application for if you're trying to heat a particular area. Lots of different reasons, or you may need to determine how much heat would be produced from a certain amount of reactant.